Can just start now. So it's my pleasure to introduce the first speaker of the morning. It's going to be Ilia Zharkov from Kansas State, and he's going to talk about tropical Prym varieties. Well, when tropical Prym is a Jacobian.
Yeah, so, well, thank you very much. Wonderful conference. And so this slide is actually, I think it's the first time I have a meaningful first slide. So there are a couple of things. So I want to emphasize the word tropical, since somebody has to talk about tropical. We are in tropics. And the other thing is fun rather than work. I think that's it's not really a work or anything. So it's just fun. Well, I don't personally. I don't think it's any work. But we'll just keep pushing. We have to finish it. I don't know why, but it's more like playing, with numbers. Another thing I want to see, so there are three meaningful things here. This art, which everybody wants to get to, I don't know how to, and this picture is actually deceiving, I believe. So we try to, with Nikita, we try to reach this beach, try to swim around this needle there, and there's no beach there. And we couldn't find it. So I don't know what happened.
Global warming.
Global warming, the ocean is rising. So anyway, so let me start maybe. So I'm gonna briefly talk about the classical stuff. Well, it's been wonderful time in the 70s when Mumford developed the theory of Prym varieties, and so here are the main definitions. So we start with a smooth projective complex curve, genus G+1, and then we consider its unramified double cover. The Riemann curves tell us that the C tilde has a genus 2G+1. Well, and the involution exchange the sheets in the cover, and well, first of all, let me say a couple of words. These covers are classified, can be classified, viewed, from various points of view. You can view them as a points of order 2 in the Jacobian. Take the line bundle of order 2, and then it doesn't have a section, but it has a double section. So that's your double cover. Or you can use a wave pairing to think about this topologically as as an element in a cohomology with coefficients in Z mod 2. That tells you, if you go over a cycle, whether you go, on the same sheet or you go on a different sheet. So that's the map to Z mod 2. And for us, I think it's the best way actually to do sort of like a mixture of the two. So if we have a Lagrangian sublattice inside, which we will have, then we can classify the things, half the thing in here and the other half is in there. So we can take the image of this class alpha in gamma, and call this gamma, or we can take, if we dualize the thing, so we can take, the image in here coming from an element in home. Alright, so what's the Prym? Well, for Prym, you take the anti-invariant holomorphic forms on the cover, and you take the anti-invariant cycles, and you just take the quotient. Usually, this is a sub variety in a Jacobian of C, and it's a abelian variety of dimension G. It's polarization twice times the principal one. So, alright, so what is known about this? Well, I'm not sure. Philip may correct me in terms of references, but it's mostly Mumford does the classification. So the question when this Prym is a Jacobian, and so the Mumford, I think essentially Mumford answered. He asked this question and he answered. So it's a good thing, mathematics. In three cases, so C is a hyperelliptic, and then the Prym splits into the product of the Jacobians of two hyperelliptic curves. C is trigonal, namely that it has a map to P1 of degree 3. Then the Prym for any double cover is going to be the Jacobian for the another curve, and there is an explicit construction for this C prime, which has a Foto 1 covered P1, Foto 1 mapped P1, and it's in the third case it's when we have a plane quintics and we have an even cover of that. The even cover means that if we take this hyperplane section and we add this order 2 elements in a Jacobian, this theta characteristic has a even dimensional number of sections. The odd ones correspond to the famous case of the cubic for the intermediate Jacobian of the cubic threefold, which I guess due to Professor Griffiths was the proof that it's not rational. Bouville extended a little bit, so I just want to mention for the case of nodal curves, so he just wants, I think it's called allowable covers, when the involution, when it fixed a point, then the sheets do not interchange by the involution. So one of the examples I want to consider for this tropical setting is this so-called Wirtinger cover, Wirtinger. So if you have C has one double point, then you normalize it, take these 2 points apart, and then you take this normalization disjoint union with itself, and then you identify these points crosswise with each other. All right, so these are the 3 examples I wanna, 4 examples I wanna consider their analogs in a tropical. And you'll see all this construction. So let me start with the saying what a tropical curve is. Well, tropical curve is a graph with lengths of the sides. The genus is a third Betti number. There is one notion I will need later, maybe a little bit. When we say 2 divisors are linear equivalent, if the difference is a divisor of a meromorphic function, which in our case it becomes a meromorphic function, looks like this. So it's a function with integral slopes and piecewise linear. So it has this is the zero of it, and this is the pole. And so if you see that, in some sense, I mean, geometrically, what you do is you can sort of move all these 3 points, the same distance, and then becomes this red points. So these are, you can clearly see that the red minus the blue is a divisor of this kind of functions. So the dimension for us is going to be, we take this definition, so if it's abstract any effective divisor of degree k, and it's still linear equivalent to an effective one, then we say that dimension is at least k. All right, that's a quick introduction.
Those lengths, so there are no lengths conditions.
There what?
Those lengths are just real numbers.
Real functions, yes, real numbers. What? All right, let me now say what's the principal polarized abelian varieties. So it's essentially, well, it is. It's just lengths. So it's a free abelian group of rank G and a quadratic format. That's it. If you want to, represent it sort of geometrically, then you can do the following. So you can represent it as a real torus, this integral structure. So the period lattice has nothing to do with this integral structure. So the period lattice is pretty much arbitrary. Oh, it has to be symmetric. This is a quadratic form. This is the way to write it down. So this is, so you take the image of the gamma. That's an element in a dual space. Then you take its dual. That becomes, this vector space spanned by gamma, and then you model it. So gamma is sort of this period lattice. So the good way to think about this is to look at actually on this form, not on a gamma, but on a dual lattice, and then it becomes so. Then any quadratic form on a lattice gives you so-called Delaunay decomposition. Namely, you just take the values of any function actually gives you this sort of triangulation. You just take the values of the function at all the points, and then you look at the upper convex hull of that thing, and then you project it down. And that's generically gives you a triangulation. If it's a quadratic form, that's a periodic thing. You can also look at the dual decomposition of the space, of this vector space. This is called Voronoi decomposition, and it's a dual to this triangulation. So this is just the names. And if you see, so maybe so on this picture, the integral structure, the way we see it. For instance, this is integral slope, this is integral slope, this is integral slope, and the black dots are, it's this period lattice gamma. So we have to mod out by this gamma to get the torus. All right. So the first example of this principally polarized Jacobian variety is the Jacobian. So you take the lattice gamma to be the cycles in your graph, and for simple cycles you just define it to be the length of the cycle. There is more efficient way to actually write it down. You choose a basis of your cycles there, and then you define the linear functionals. But for every edge on a graph, you orient it, and then you look at how many times the given cycle passes away. So this defines LE defines a linear functional on a space of cycles there, and then you can write this in quadratic form in this way. So this is length times the linear functional square. And you see that the choice of the orientation doesn't matter because it's squared. Now the one important point I want to stress here, this is dicing. The dicing is a lattice where you can write. If you can of course write any quadratic form in terms of a positive number times some linear functional square. But the dicing is a special thing that all this LE form a totally unimodular system. So if any number of them form a basis, then this is a basis of the zeros. This is equivalent to say, you can say that this Genealogy decomposition is given by the families of parallel hyperplanes, and all those hyperplanes intersect the max. If they intersect in a point, then this point has to be a vertex of a lattice. So this is just an example of next dimension. This is the curve of genus 3, and this is the Voronoi cell there. And the dicing, and our lattice is given by this, six vectors. It's called A3 lattice. So right, so let's go to double covers. So double covers are a little bit tricky on the tropical side. There are two types of unramified double covers. The first one is called simple. It means that every point actually has two clear pre-images. So if you see here, and every point has two pre-images. And the way to encode this double cover is maybe put some crosses on some of the edges. That tells you that you just take two disjoint unions of these things downstairs and break it here and glue it crosswise. That's the way to encode the double cover. But there are also other type when you have a sort of the other type is when you have a sort of a thick edge mapping just one edge with degree 2. So it means sort of we can think of this tropical curve sort of as being the base of the vibration by circles, and this thick edge is that every fiber maps 2 to 1 to the circle downstairs. So, oops. But then the condition that's this thick edges have to form a simple cycle. This is Riemann Horowitz, I think, again in English. So, and now we have a problem with these non-simple ones. That for every simple one, there is a unique way to for this picture actually to lift it to the complex double cover, for the complex curve. But for these ones, for instance, there are many ways to lift it, and that number of lifts is actually, we essentially lifted every, for instance, this one lifts to, what is it, four possible ways, because the complement of the gamma is just one interval and it has no genus, so this double cover, this tropical double cover leads to four complex ones. Okay, now let's do the tropical Prym. Everything is the same, so we look at the anti-invariant cycles. Well, okay, who are they? It means that when we look at the double cover, the anti-invariant ones, those which are sort of two disjoint unions of the cycles. When we lift the cycle from below, that has to come, two disjoint cycles upstairs. That means that the cycle has to be even, so it has to cross even number of crosses, and sort of a similar condition for non-simple covers. I won't pay much more attention, to non-simple covers because they are less interesting, obviously. Quadratic form is more or less the same. You just calculate the length of the cycles. You have to be a little bit careful with which orientation you take when you cross the edge. Sort of this orientation of the edge switches. So. All right, so let's go to this 1, 2, 3, 4 cases here. I'll start with the last one. So classically, high genus curve Pryms are never Jacobians. So that is not what's happening in tropical case, and the reason is we'll just take this simple case. So if you take any tropical curve and you just put one cross on there, then the Prym of this is always going to be the Jacobian of the curve when you just take this edge out, because all the even cycles are those which do not pass through this edge. So we just effectively can remove this edge. And that corresponds to the case, if you think about it, this also comes from degeneration of the Wittgenstein cover. So this is why it becomes Jacobian. I think that's an explanation. Let me go to the hyperelliptic case. So, all right, there are two kind of hyperelliptic curves. So the hyperelliptic curves are those which have 2-to-1 map to T1, ramified in this case. So these are, these vertical things are the ramification, and the P1 is this tree downstairs. So that's a map, from this thing to the downstairs tree. That's a map from a hyperelliptic curve to a G. And then if you put some crosses there, you can always, push all the crosses, for instance, to the upper thing. Then this collection of crosses divides all this, connecting vertical rods in two classes. The classes, the rods in the same class, they have even number of crosses apart. So, and if you think about it, we can write this big curve as a union of the two when we take only, the same upstairs and downstairs trees, but we can connect them only using, red rods or the blue rods. So this is a red curve and this is a blue curve. And it's easy to see that the Prym actually becomes a product of the Jacobians of these two. And maybe this is an explanation for that. But the point is that if you look at any edge here, this edge and the similar edge upstairs, if you take the red cycle or the blue cycle, these two edges count with, for instance, for red ones they count with opposite signs, but for the blue ones they count with the same sign. So it's always, each pair of edges for one type comes with the same sign, and for the other type comes with the opposite sign. And this is the wonderful quadratic identity, which, so this is the Prym part on the left-hand side, and this is the Jacobian on the right-hand side. So maybe I'll say a word about non-simple covers. Sorry, simple covers, but of non-letters. There are also hyperelliptic curves like that when you have, this is a map to just a line. I'll just take a local piece of it. It's a double cover over there, but then it's again, so this edge here maps to the edge downstairs with this, torus, and with this circle bundle mapping 2 to 1. So it's like a thick edge here, which maps to the. And then this edge has a color, and we just take, if it's a blue curve, then we take this blue curve with the blue edge, even if it's a red one. And again, the point is that now this edge comes with if it's a blue edge, then it comes with the opposite sign, going this way, cycle, and going backwards. This edge counts as plus and a minus. This is why we have it, Every cycle here again goes this way and then comes back along the same edge with the opposite sign. If it's a red cycle, on the other hand, for instance, if you take this red cycle, there's only one red cycle here, then this edge actually going one way and coming the back way, this edge enters with the opposite orientation. We come downstairs and then come back upstairs. So this is why this edge actually, splits in two edges like that. So again, if you count the genus, that's the right count. All right, so let's go to the second case. Trigonal. So again, I'm just gonna consider one case here. So we have 3 edges mapping to just a single edge of E1 downstairs, and then all these ramification points. They, we can put a little rod here between the edges, or we can put a little rod there. So this is just a local trigonal curve. So where do we get a trigonal curve? Well, we fix. Now we have 4 types of vertices. So we can fix one of them, and then the colors are, if you move from that fixed vertex, depending on how many crosses we cross on H1, on H2, on H3. So this is Z mod 2 to the power 3 ways to cross, to put, to cross from one ramification point to another one. But if you, for instance, if you put all 3 crosses, then this is the same as no crosses. So you have to mod out by the diagonal Z mod 2. And this actually sits inside as 4. Well, I just showed how 1, 0, 0 maps to the. So we switch 1 with 0 and the other pair also. For instance, 1, 0, 0, 1, 2 would go, 2 is switched with 0 and 1 is switched with 3. So this Z mod 2 squared group sits in S4, and that's how we put the rods in this trigonal curve. Again, so maybe it's too quick, but the key observation is again some quadratic identity. Think about this top line is the Prym part, and the bottom line is the Jacobian. All right. So, all right. Now, before I go to plane quintics, this is the most interesting case, of course. Plane quintics. Let me say a couple of words. What's the tropical theta characteristics? So for the theta characteristics, well, of course, there are only 2 to the g of them, not to the 2g. There is only one non-effective one. There is only one, generically there is only one even theta characteristic. This is this Riemann constant kappa. So if you degenerate your complex curves, all the complex theta characteristic which converge to that tropical one, they're all even. So there are 2 to the g, complex ones which have, which sits over that special tropical one. over every other theta characteristic, there is always, half even, half odd. So let me just describe quickly how you draw this, where do you find this theta characteristic. So you just pick a point, or maybe any finite set on there, and draw the distance function, and draw the gradient flow of the distance function. If you have, for instance, one point, another point, and then the distance between this point somehow becomes equal, this is where you have the bend in your. This is where you have the valency of this is 2, and you subtract 1. So generically, if you just have a distance gradient flow, that it always has every point has one incoming and one outgoing. So it's always this mostly 0 for all the points. But for some points, this becomes +1. And it's -1 at those points which are in this set S. So because you point in a set that both gradient lines are outcoming. This is non-effective. You can prove it. The other ones are effective, and they are given by the distance from every simple cycle. So if you pick, for instance, like a cycle in your curve, and then draw this distance flow from that cycle, that becomes again a theta characteristic. So that's the way to give bijection between the points of order 2 in Jacobian, in tropical Jacobian, with the theta characteristics. Because we have a preferred, this never happens in a complex case, right? So we have a preferred theta characteristic. All right, another digression before I go. I have to say a couple of things about 5-dimensional lattices. Well, this is a wonderful subject. You can spend years studying. Some people do, I guess. So I'm gonna consider only dicings. So dicings, 5-dimensional dicings are classified. Maybe I'll say a word about 2-dimensional lattices, all dicings. 3-dimensional lattices are all dicings. 4-dimensional lattices are not all dicings. There are 2 maximal dicings in dimension 4. Dimension 5, there are 4 maximal dicings. And they've been classified. So the first one is the basic one which exists in any dimension, of course. It's type A. You just take these basis vectors. They form a totally unimodal system, of course. The good way to visualize this unimodal system is to put all this. They call zone vectors because if you add them, then it becomes the zonal, which is the coordinate cell. There are you put them in this K6 the graph, and then there are obvious relations between these vectors. For instance, if you have a triangle here, then the sum of this thing is 0. So this is a very good way to record the relation among these basic vectors. All right, there are okay. So these are our 2 planar graphs. There are 4 trivariant graphs of genus 6. Genus 5. 4 types. 2 planar. Every graph, of course, has its Jacobian, which is a 5-dimensional lattice. So we can identify, every planar graph, of course, is a sublattice of this A5 because we can order, choose the basis of cycles, just this cycle, this cycle, this cycle, this cycle, this cycle, and then you see that every edge enters it exactly, either 1 or 2. If it's 1, that's the basis, and the basis element. If it's 2, that is +1 and -1 in the other one. So this is clearly, a subdicing of the A type. Every planar graph is a subdicing of A type. So if you look at this, so this is a little calculation you would have to do. So it's obviously have 12 edges, so it has to have 12 zone vectors. So which 3 do we remove from the 15? Well, this one has to remove the 3 which go 1, 2, 3, and they do not. So this is a length 3 Broughton line, which doesn't connect. The other one for the cube. For the cube, we remove 3 non-intersecting vectors there. two, they are not maximal, but they are dicings, and they come as a Jacobians. There are two non-planar graphs, and there are two more. I think this is quite amazing. So there are two more dicings which are not, this is actually maximal dicings. So I didn't list, the basis vectors. So there's 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. So there are 5 basis vectors for each of those collections. So there are 12 altogether, and these are 7 more. So there are 12 zone vectors there, and 12 zone vectors there. And those are maximal dicings, and they are Jacobian. Well, I'm going to consider 2 more dicings, which are actually sub-dicings of A5 again. They will come up for my plane quintics. So, all right, so here I remove a triangle, and the other triangle, which is complementary to triangle, I impose that the length of these things, the coefficient at L square, each edge here is like a linear functional, and it enters a square into in my quadratic form, and I impose that this coefficient at these 3 things is equal. So out of 12 zones here, the 3 which form this triangle have to have the same coefficient. So it's only a 10 parameter length. And this is a degeneration of this one when I completely remove this other triangle. Let's call this G5. This took me some time actually to show that this is not a Jacobian. So this is a non-trivial statement. Maybe, well, it's not hard, but again, it's fun, right? It's not work. This is not a Jacobian. What is easier is to show that the one which is this famous one, E5, is 10 zone vectors. This is the 4th maximal dicing in dimension 5. It has 10 zone vectors. This is easy to show this is not a Jacobian, because if it's maximal, then we cannot add any more vectors there to still be dicing. So, and every graph comes with 12 zone vectors. So you see, this is impossible to be a sub-dicing of a Jacobian. So this is not a Jacobian. All right, so A5, G5, F5, and E5. G, E, F are not the Jacobians. All right, let's now talk about plane quintics. So I'm going to be, I think, in share addition here to finish the first talk. So okay. So who is plane quintic? It's not a plane quintic, planar quintic. It's actually it's a tropical plane quintic, which for me is going to be a curve of genus 6, of course, which has the following property. So it has 3 disjoint cycles, which are responsible for, this is the theta characteristic, the one which gives you, dimension 2, the one which gives you, classically embedding to B2. So it has 3, why is it 3 disjoint cycles? Well, if you remember my way to define the theta characteristic, so these points are where, this point is equidistant from this one. This is where I have, my point in a theta characteristic. So this is where these 2 gradient lines meet. Same thing about, the other 4. So there are 5 points where the distance, the points which are equidistant from one of, from the 2 of those 3 cycles. There are 5 points. This is the theta characteristic by definition. And why is it? Why do they have to be 3 of those? Well, because if you think the hyperplane section actually cuts your tropical curve into, cuts the plane into 3 parts. So if it cuts, so if you try to draw the hyperplane which cuts your curve, then it should cut it in 3 parts, and then every part should contain one of those blue cycles. So there have to be 3 blue cycles, and the condition is that this divisor is dimension 2. So you have to do a little calculation here. For instance, this divisor having dimension 2 means that, for instance, this edge here has to have the same length as these two combined. And the same thing, this edge, for instance, has to have the same length as these two combined. So, and this, and for the third one too. So this is out of 15 edges here, 3 relations. So this gives you, this 12-dimensional freedom. Okay. Now let's. Well, there are lots of types of that, but most of them are degenerate. So I just want to consider most interesting ones. So when we have, how do we connect these 3 cycles, these blue cycles? There are essentially 3 interesting ways to do it. This is planar, this is planar, this is not. It took me actually a while. So where do I get a non-planar graph by a planar quintic? And if you think about it, so if there is a tropical plane, it's not necessarily like a plane, right? So it can be this hyperplane in R3, and it's actually fairly easy to see this graph sitting inside this tropical hyperplane. So it's not a planar graph, but this is the most interesting one. All right, so let me do the classification, I guess. So again, for every type we have 64 possible colors. But you have to notice something. Yeah, I didn't say. So one important thing. So if you try to translate this theta characteristic being even or odd into tropical thing, then that turns out to be, for simple colors, this is actually easy because every simple color has a unique complex color over it, and every theta. Of course, for every tropical theta characteristic, then we have to for every tropical double cover of the tropical simple double cover, we can associate a complex double cover uniquely, but only for simple ones. And so, a little calculation tells you that the complex theta characteristic, which is defined uniquely from the tropical one in this case, is even if your this cycle eta. Remember that's a cycle with values in Z2 on a homology of our graph is odd on these 3 cycles. So and vice versa. So for instance, if you just have one cross over there on one of the blue cycles, for instance, on this edge here, there's going to be an even theta characteristic. All right. So how many crosses we can have? We can have 3, 2. I mean, depending on the. So we have 3 cycles. They can be, each one can be even or odd. So if all of them are odd, namely the eta gives you 1 on those, that's the. You can calculate it. It's a Jacobian of this genus 5 curve. So it's a cube here, it's a cube here, and it is twisted cube over there. Well, so this is twisted of that, so it should be twisted. Oh, I know. So actually, in this case, in the middle case, you see anything? Yeah. In the middle case, all these things actually degenerate, so they are always sublattice of pi. I guess unless, except this case with this hot the others are non-degenerate. So anyway, so this is the complete classification which I did for fun, and it tells you precisely what you expect. So it's a Jacobian in the case of 3 and 1, and it's not a Jacobian in the case of 2 and 0. And again, so there is some beautiful identity, and it's sort of not very non-trivial.
Do you want this?
Very non-trivial. It's a bit of trivial identity, which trivial identity, but it's sort of you have to, when you do the calculation that you have to use. And all right, so maybe I'll say a word, keep it three-folds. You can actually do this thing with three-folds, but the first time it appears in the work of Vienna, he was a student of Alexeev, and Alexeev apparently taught him to do that. So he considered the cigarette cubic and project from a line, and then you see your quintic being 5 lines, and if you calculate the double cover associated to these 5 lines, then so these 5 vertices are the 5 lines. This double cover actually has a cross on every edge here. So if you go, for instance, over the triangle, this is an odd cycle. So to get an even cycle, you have to go over quadrilateral or hexagonal. So those are the even cycles, they 5-dimensional. And so he calculates this lattice being E5, which is again not very hard. It's not a Jacobian. So this is sort of an alternate proof of this result. Very quick and easy. Well, I mean, it's weaker in the sense that it proves that every generic threefold is not a Jacobian. So I guess I'll stop here. Thank you.
Questions?
So classically there is this problem about the equations defining the Prym varieties in the principally polarized area.
There are many
Does
questions.
it make sense in this tropical?
I mean, everything makes sense.
Yeah, but the equations defining the locus of Prym.
No, the equations. I mean, they're going to be, in tropical, everything is, piecewise linear. So every polynomial, for instance, becomes a piecewise linear function. So I'm not sure is that what you want. You can get some understanding of the behavior of this, but not exactly the equations. You will never get the same equations. But you can get some understanding of the behavior of the geometry of that. I mean, there are many classical questions. For instance, this Chiesa locus, which when the Abel-Jacobi image of a curve and minus the Abel-Jacobi image of the curve are algebraically equivalent. This is also like an open problem, I think. So you can try to answer it tropically, but I think the tropical. I mean, the slogan of tropical geometry is that when something goes wrong, when something is true algebraically, then it should be true tropically. For instance, if you want to prove Hodge conjecture, you cannot prove the tropical Hodge conjecture and deduce it. But if you want to disprove Hodge conjecture, then you can disprove it tropically, and that's gonna disprove the classical ones.
Any further questions? Okay, so
was Joe Harris and Eisenbud, did they use this, but in effect, for tropical constructions for the Brill murder thing?
I know there are people, and not Harris and Eisenbud, but there are, I think, some students of them, like Sam Lane, for instance, and other guys. They do this brilliant stuff for tropical curves and deduce something about. But again, you only get sort of the lower bound in some sense. So, I mean, one of the bounds, not that exact. And again, so it always works. Anyway, everything can be addressed tropically, but you have to have a family. So it's if you have, like, for instance, if you have a K3 of rank 20, right? So you cannot see it tropically because this is it's not in a family.
If you have a K3?
Yeah, of rank 20. Quartic in P3 of Picard rank 20. You cannot see it tropically because it's a single point. It doesn't live in a family. So tropically you only see phenomena which lives in a family, because you have to degenerated. That's roughly the idea.
So a tropical surface is what?
Tropical surface is in P3. It's this polyhedral complex of dimension 2 with some.
But is it
condition.
just simplices, or do you allow cells?
No, there are polyhedral cells, not necessarily simplices. But they have to come, with this balance, so to say, balancing kind of addition along the edges. So this 3 would have to the sum of the outgoing vectors have to be 0 modulo the edge.
Okay. No more questions? Let's thank our speaker again.